Hello guys, in this video we are going to see an application of functions, okay? It's called impulsive maneuvers and it's a very practical way of working with functions. In this topic we are going to deal with many things and I prefer just talking about something that could be practical in your life rather than talking about x squared, x cubed or functions that they are important but you need much more time to reach an important or practical applications. Let's see impulsive maneuvers and which are the objectives of this video. Okay, we will try to understand the fundamental principles of orbital maneuvers. Perfect. We will focus on impulsive changes of the velocity, the velocity in this case. We will learn how to calculate the change in velocity. We are going to call this delta B, and it's an important notion in orbital mechanics. We are going to use the rocket equation, and we will apply this these ideas or concepts in a practical example. Okay, requirements. Be careful. Here I wrote basic understanding of physics and rocket propulsion. Okay, not so much. We are going to see this from a practical point of view, just from the mathematical point of view, and I'm not going to enter with many physics problems that can make this exercise really dangerous. So we will just see the main ideas of rocket propulsions. Familiarity with logarithmic functions and their applications, yes, we will need some working with functions, as you know, makes necessary to remember some ideas of functions. Okay. That is the reason I'm going to use these definitions and topic in this video. Okay, let's start with what is an orbital maneuver. An orbital maneuver, it's a specific change. It's a change. This is the main idea. Change in the orbital elements when a force is applied to a spacecraft. Okay, I mean, you have a satellite orbiting on the Earth, for example. And then we're going to just push this satellite in one direction. This is an orbital maneuver. Depending on how we apply this maneuver, this is the orbit of satellite is going to change in one way or another. It's very dangerous, by the way. Okay, you cannot just push anything in the space and okay, let's just for the fun. Okay, no, be careful. It's very dangerous. Okay, we are going to consider only propulsive forces. I mean, you are going to have a rocket, and this rocket is going to just open the engines, and the thrust is going to push the rocket in a direction. But we are going to consider impulsive maneuvers. What does this mean? That the time you got the engine on, it's very small. Very small. We are just thinking about like pushing something in the space. Okay, it's very short propulsive force. Okay, I don't want to have the engine on, for example, for 20 minutes. Okay, we are just going to talk about an ideal case in which we just can just put the engine on 1 second, and then the spacecraft is going to change the way or the orbit in which it moves around the Earth. Okay, orbital maneuvers can be classified in two types. The first type is called pumping maneuver. It's when we change the magnitude of the speed of the velocity vector. It's when we only change the speed, not the direction. Okay, if the rocket is going this direction, something pushes me from the back. Same direction I go. The other type is called cranking maneuver, and in this case we change direction. It's like if you are walking in the street, someone came and pushed you in one direction, and you just fall in another direction, in the one direction you were pushed. Okay, so when you change the direction of the velocity vector, then it's called cranking maneuver. If someone is just pushing you faster in the same direction you were moving, it's called pumping maneuver. Okay. Perfect. How do we calculate a change in the speed or a change in velocity? Remember that the key idea is called delta B. This is the difference between the previous velocity and the final velocity. it's a very short definition. Okay, and we are going to relate the variation in speed with what we call the rocket equation. Tsiolkovsky name, it's a Russian name, it's very hard for me. Tsiolkovsky, sorry. So what is this rocket equation? By the way, it's very old equation, it's a very old equation, and it's still applied in order to calculate the maximum speed a rocket can reach. Okay, so it's a very interesting function. And we are just consider this equation. This is a physical equation, has influence in reality, but we are going to see it from a mathematical point of view. For me, it's just a function. Depending on what? Okay, this function depends on 3 parameters. The first one is B sub E. What we call is the effective ejection velocity. It's the speed the rocket launch the propulsant. Okay, you have a rocket and it's always ejecting something to push the rocket up. Okay, so this is the effective ejection velocity. It has something to do with the type of rocket. We can change that, but normally a rocket has a specific effective ejection velocity, and depending on the rocket you use, it has different numbers. Okay. More elements. M0 is the initial mass of the rocket. Mf is the final mass of the rocket. And we are going to call Mp is the propellant mass of the rocket. It's the propellant that the rocket has and it's going to be ejected or burned during the process. Okay, as you can see, the rocket equation is just the effective ejection velocity times the logarithm of the initial mass divided by the final mass. If you want to simplify this a little bit, this can be written as the initial mass divided by the final mass minus the mass of the propellant that has been burned, okay, during the process. Perfect. Let's see an example. Imagine that you have a vehicle with 7,000 kilos, of which 900 are propellants. Okay, if the engines have an effective ejection velocity of 3,000 meters per second, is an speed, we'll have a delta V of, let's see, we are going to put the ejection velocity in front, logarithm of the total mass, the initial mass of the rocket, divided by the initial mass of the rocket minus the kilos of propellant. Okay, we are going to think that we just going to burn these 900 kilos. Okay, so what is the delta V that this rocket can reach? Okay, if we simplify and calculate, any calculator can help. It's 412.86 meters per second. Is this much? Yes, it is, of course. In kilometers per second, it's going to be 0.412. Seems not so much, but okay, be careful because we are talking about divided by seconds, okay, and this is a very high speed. Okay, this equation, rocket equation, can be written in a different way. It's related, and it can be proved that this is the same. But look at this. We change the ejection velocity by something called the specific impulse of the propellants and the acceleration of the gravity at the sea level. It's the equivalent part to the ejection velocity, but in this case it's more common to talk about the specific impulse. By the way, the definition is written here. The specific impulse is the period in seconds during which 1 kilo of propellant mass will produce a thrust, a push of 1 kilo of force. Okay, it's at least it's not intuitive definition, but guys, rockets, if you just look, you go to internet and look for different kinds of rockets or propellants or engines to push or to thrust a rocket, you will see that they talk about a specific impulse. It can vary from 300 seconds, 1,000 seconds, and depending on the specific impulse, the rocket can reach a higher speed or not. Okay, so in this case, we can just solve an exercise. Oh no, be careful. Before we do that, okay, why I'm showing you this function? Let's use this function in a different way. As you can see here, I have the initial mass and the final mass. If I give you an example, I will provide the value of the specific impulse and the gravity velocity at the sea level. Okay, this is just to replace and calculate. But can we know, given the delta V, given that I need to reach a speed, for example, 7 kilometers per second, do I know how much mass of propellant I need? Okay, this is due to this function. I'm just solving for this quotient here, okay? ISP, the specific impulse, and G0 is going, I move this to the other part and they come dividing. The logarithm, I can solve it just changing by the exponential function. So this quotient can be written as the exponential function power the change in speed divided by the specific impulse and G0. But at this point, we have the initial mass and the final mass. I would like to know the change of mass I'm going to need. And remember that this is going to be only propellant, mass of the propellant, okay? So I can just write this expression, just calling delta M as the initial mass minus the final mass, and I'm going to call this delta M, okay? And this equation can be written like this. It's very easy, guys. It's nothing, just by replacing things and simplifying. This negative comes because the exponential function is turned upside down. Okay, I just flip it. Okay, and therefore, if you simplify from here, the change in mass can be calculated as the initial mass times 1 minus this expression. Okay, but you are going to be given everything. I'm going to give you the what is the change in velocity, the numerator. I'm going to give you the specific impulse, the denominator, and everything else. So you can know how much fuel I'm going to need in order to make a change in the orbit. Okay? I have an example here, a very fast example. I'm not going to spend much more time. Imagine that you want to go from a low Earth orbit to a geostationary Earth orbit, okay? And you need 4.1 kilometers per second change in speed, okay, in order to go very far from the Earth. Okay, if you have a 2,600 kilos of mass in your rocket, and the standard gravity is 0.00981 kilometers per second squared, then you can just replace everything in the function and calculate how much fuel I'm going to need. As you can see here, I just changed the initial mass by 2,600. Delta V is 4.100. Be careful, okay? It's not. There's a missing dot here, and divided by the specific impulse G0. At the end, we are going to need 1,732 kilos of propellant. Not bad, guys. Not bad. Okay, what have we seen today? We just started introducing what is the delta V, the change in speed. Still, we don't know how to apply it in order to change orbits, but at least we have an idea that it provides the value of change in speed in order to make something happens in the space. And also, the rocket formula, the rocket equation that we can use in order to calculate the final speed we are going to get, or using the alternative formula, the mass, the fuel mass I'm going to need to make a change in space. Okay, I hope you find this helpful, and thank you for your attention.